So we just finished talking about this production function. And so it takes these inputs and relates it to the output. Right? So that's what this f does. And this f one here is all of the things that might be explaining the student's educational outcome that's not explained by the production function. So for example, if there's a recession, right, that's going to massively affect wages, right? But the recession might not affect the class size, or it might not affect the teacher quality, right? So you had a lot of people that came out of, that graduated during the recession in 2008, and they just lost their jobs. Nothing happened with their inputs. They had the same inputs as the people from the year before, the same law degrees from really fancy places, but the jobs just were not there. And so that epsilon, for example, could take that into account. Okay, so let's talk about some typical assumptions on the production form, on the production function, sorry. Okay, so this will be interpreting I'm going to go all the way over here, because that might be weird. Some people might be freaked out of this. Because there's the advantage of it being very close there, but then some people need to read left to right. So, okay. So let's go. Interpretations of the production function. So, typically we assume a linear production function. So we have, so for example, yi would be equal to beta 0 plus beta 1 x1, input 1 for person I, plus beta 2 x2, input 2 for person I, plus epsilon I. Okay? So typically we assume a linear production function. And I should add some more words here. We assume a linear production function. This is in the inputs. Okay. All right. And we also assume separability. And what that means is that I take input 1 and then I add it to input 2 to produce the output, and they independently, the additive separability property just means that, so it's linear in the sense that we just have x instead of x squared or log x for each of the individual x's, and then the separability just says that they enter separately. So an example would be, take cereal, right? Like in order to produce a bowl of cereal, what are the two inputs that you need? You need milk and cereal. Okay, what if you only had milk and you produce cereal with just milk?
No.
No, right? Because you need the milk. Because the production, the output is like how many bowls of cereal, right? And it's like how much milk and how much cereal, how much milk and how much cornflakes you have, right? And so the production function for cereal would not be additively separable. Because if you have 0 cereal, you can't produce a bowl of cereal. If you have no milk, you can't produce a bowl of cereal. Right? But this is something more like, this would be like more akin to like money. If I said like, how much money do we have in the whole class? And the production technology that we used was a tax. And I came around and I taxed each of you 10% of whatever's in your wallet, right? And so this would be, these betas would be like, for example, the tax that I levy, for example, on a given person. We can say, how much did you give, how much did you give, how much did you give? And we can add all of that up. Because money is money, we can just add it all up. And so that's an assumption that we're going to be imposing on all of these inputs. That somehow changing the class size is going to have a separate effect on, the student outcome apart from changing, say, for example, the peer quality. And that's a very strong assumption to make, right? Because if we have a larger class, the peers may act very differently. Right? So if you're in a larger class, you might be more anonymous, where if you have a smaller class, you might actually be a lot more engaged. And so this production function that we're specifying here has a lot of limitations. And so I just want to talk about that. We could capture that by introducing some nonlinearities or by introducing some interactions between the inputs, which is something that we can use to take the analysis further. But let's use this as a baseline. This is like kind of the simplest possible production function we can have. Okay. Now, if we look at, so let me ask this question. What is the interpretation of beta 1? Who can tell me what the interpretation of beta 1 is? What is the interpretation of beta 1?
So the percentage change in yi when x1i increases by 1.
So what would we need? What would we need to be? Now look, this x is linear. Okay, so let's go with that. Let's see. So if we do dy dx1i, what is that equal to? That's equal to beta 1, right? And so we can rewrite this as like some small change in yi over some small change in x1 for person 1 is equal to beta 1. And that's just going to imply that delta yi is just beta 1 times delta x1 for person I. And so what this is telling us is if we change the input by 1 unit, we're going to get beta 1 more units of output, right? And so the interpretation here is different from the interpretation of the minter wage regression, because in the minter wage regression, we had the log of wages. And so that's actually a really good point. So like the minter equation would be separable because everything acted separately, but it was not linear, right? Because we had like experience squared, for example, right? So this beta 1, so beta 1 is the marginal product of input 1, i.e. output changes by beta units for a 1 unit increase in input x1i. Input x1. The I just is an indicator for the person. Okay, good. Okay. Oh, good, good. Fantastic. All right. Now, okay. So we talked about this linearity assumption, and we talked about the separability assumption, right? And so we can address the linearity issue by, for example, looking at the log of inputs or looking at some other function of the inputs, right? And so let me type this. How to relax the assumptions. And the importance of being able to relax the assumptions is because we don't want that the results depend on the assumptions that we make. We want these results to be robust or like independent of the assumptions that we make, right? Because it could very well be that a really small class size, like going from like, who thinks that going from 300 students to 301 students has a bigger effect than going from, let's say, 9 students to 10 students? Thinks that has a smaller effect. Yeah. So that's an example of like this whole nonlinearity thing. So go back in your notes and look at when we did the interpretation on the experience squared coefficient to really understand like what the nonlinearity is doing. So for our linearity, we can introduce nonlinear. So for example, we could have yi equals beta 1 plus beta 2 log x1I plus epsilon I, right? Or we could have beta 1 plus beta 2. My apologies. Let me make this beta 0. This beta 1. Okay. So that's how we can relax this. And we could also make this x squared, x cubed, and so on and so forth. We can introduce a polynomial in x1. So that's one way that we can do that. For our separability, we can include interactions. Between for those of you in the back, can you see my right? I'm going to write over here. I'm going to write all the way here. So for example, we could have yi is equal to beta 0 plus beta 1 x1I plus beta 2 x2I plus beta 3 x1I times x2I. I'm going to let you write that down. And so what we've done is we've introduced it's still going to be linear in each of these x's, but then we've created an interaction between x2 and x1. So for example, it could be the case that in our example, we said that x1 was going to be pair qual. x1 was going to be class size, and x2 is, what was x2? From our notes? Teacher quality, right? And so we might imagine that what happens is, as we change class size, then the impact of class size varies with teacher quality. So if you have an amazing teacher, right, increasing the class size might do nothing to change the effect. Let me step back. If you have a really amazing teacher, right, the effect of the effect of output on class size might not matter very much, right? But for like a really lousy teacher, it could be that like reducing the class size like improves student performance by a ton, because that teacher needs the ability to focus on individual students, and that's what this interaction trend is going to capture. So for example, here, if we look at so let's compute the marginal product of class size using, let's call this equation star, using the production function and star. So when we do dyi dx1I, what is that equal to?
P1 plus P3 x2.
Beta 1 plus beta 3 times x21. Does that make sense? And so what's going to happen is, so what's the interpretation? What's the interpretation of this?
This is beta 3.
This is beta 3. Thank you. That was a mistake. So this is beta 3. And so what this is telling us, so for example, let's suppose that beta 3 is positive, right? Then what is that telling us? What is that telling us? If beta 3 is positive, what does that tell us about the marginal product of, what does that tell us about the marginal product of x1? Okay, so suppose beta 3 is greater than 0. So beta 3 is greater than 0, and also beta 1 is less than 0. So class size is bad, right? And this interaction term between class size and teacher quality is going to be positive. It's going to be negative. What does this tell us about the marginal product? Of class size. And I'm not saying that this is what is happening in reality, but we're just going with the model to try to understand what's happening. So what does that tell us? Okay. So this is teacher quality. So if teacher quality is equal to 0, what's going to be the marginal product of, what's going to be the marginal product of class size?
0.
Say it again? 0. No, because teacher quality is x2. It's going to be beta 1, right? Because this here is the marginal product of class size. Does everybody see that? No? Who's tracking me? Okay. So this is the marginal product of class size. The fact that beta 1 is negative is telling us that larger class sizes lead to worse outcomes, right? The fact that beta 3 is positive is telling us that if we have, as we increase teacher quality, a larger class size becomes less of a problem because we have this negative number plus something that's positive, right? And so to put this into perspective, and if this is confusing to you, please, like go through it in your groups. So like imagine that, so this is 0 here, right? This is beta 1 equals minus 5, right? Now let's say beta 3 is equal to 2, right? So this is beta 1. So then beta 1 plus beta 3 times x is going to be somewhere here. So for example, if x is equal to 1, you'll get minus 5 plus 2 times 1, which is going to be minus 5 plus 2, which is minus 3. And so what would, I mean, like you don't have to like write this in your notes, but this is just to explain it conceptually. So what this is saying is that the effect of class size on student outcomes is negative. But if we look at a class size that has a better teacher, the effect of class size on outcomes is going to be less negative because that better teacher is going to be able to mitigate the direct effect of class size being negative on the output. Whereas if you had a worse teacher, like if X were negative and the teacher had like a negative quality, then you actually have the effect of class size being exacerbated because this person is a bad teacher to begin with, and then on top of that you make the class bigger. So the effect of making the class bigger, this is saying that the effect of making the class bigger for a worse teacher is more negative. But for a better teacher, it's less negative. So that's what this interaction does. And going back to this example that we had where we said, look, the difference in, going back to this example where we looked at, well, is the class size going to be different for different teacher qualities? This kind of makes sense, right? That in general, it may not be the case that the effect of changing class size is going to be the same independently of like what the teacher quality is. So that's the idea. Any questions on that? Okay. Yeah. I'm going to talk about, so we talked about this. We're going to talk about the value-added approach, and then we'll finish off with the hedonic approach. And the value-added approach is like very similar to this. So what I'm going to do is I'm going to erase these two boards here. Does everybody have these two boards here? Does everybody have this in this board? Okay. So one of the things that we don't account for is we don't have the ability of the students, for example. We don't have their unobservability. So the outcome can be affected by like, did the student like learn how to read in kindergarten versus not? And if we don't have a measure of that, that's a really important unobservable because that unobservable can be related to a lot of things, right? So like maybe something that could happen is that you take all of the students that are really, that were not able to read, and you put them in a remedial class. And if the remedial teachers tend to be much better than average or much worse than average, then you can get this correlation between the student ability and between the beta, between the actual input that you want to measure. So the question is, how can we take care of that? So the value added model. Okay. So suppose we have measures of student output over time. So for example, we have yi at time equals 1, yi at time equals 2. And so we observe this kid in like kindergarten, we observe them in first grade, and so on and so forth. Right? And we also have measures of input over time. Have x1 of person I at t equals 1, and so on and so forth. Right? We can write out a production where output for person 1 in time period t is equal to some like alpha I, where we say this is the, let me use the AI, which is the person's ability. And we're going to take this ability to be the same across all time periods, right? Plus beta 1 times x1 input 1 of person I in time period. Does that make sense so far? And so now what we can do is, this is plus epsilon I. Now this ability is unobserved, but it's constant across time. So what we can do is we can say, let's take yi t equals 2 minus yi t equals 1. And when we take this difference, the ability is going to drop out, because we have AI, this is only dependent on the person, plus E1 x1 I t equals 1. Right? Plus epsilon 1. Epsilon I time t equals 1. Minus AI plus beta 2 x 1 I equals, these indices are wrong, this should be 2, my apologies. This first index is time period 2, t equals 1, plus epsilon I t equals 1.
On the bottom, should that just stay as a beta 1?
This should be beta 1, yes, thank you. There are a lot of indices here, so please do go over this when you go home. Let me give you a moment to write that down. Does everyone have that so far? Okay. So what we've done is we've said this is the relation. So this is the relationship that holds between inputs and outputs in each time period, right? So this is the input output relationship in all time periods. Right? We have this unobservable AI, and so we just take the difference between the two time periods to remove that, right? And so the issue is AI is unobserved. For constant across time. So we just take the difference between outputs and two time periods. And so what we end up with is delta y I, and this is between time period t equals 2 and t equals 1. And when we take this difference, the abilities cancel out, right? Just put your pens down for just a quick second and just look. Just put your pens down, everyone looking at me. All right, so we're just taking these difference here. This AI here is going to cancel. We have beta 1 x1I t equals 2 minus beta 1 x1I t equals 1. So we're just going to get beta 1 times the difference in the two x's, right? And then we're going to get the difference in these two errors here. Now, since we have put in, we've modeled the unobservability, we've taken out of the residual the part that's unobservability. And so anything that's left over here is not going to be related to unobservability. And so this is simply going to be just beta 1 times the difference in x1 for person I plus the difference in the epsilons for person I. And that's going to be it. And so now what we can do is we take the data, we take these two differences, and now we can run this regression, and we can get a beta 1 that's unbiased. Does that make sense? And that's what's then in the value-added models. Because what's happening is that the basic assumption is the student isn't changing over time, but the inputs that the student is being given are changing over time. And so any changes in the inputs are going to be driving changes in the outputs. And that's the basic idea behind the value-added model. What we will do next class is we will pick up with the hedonic model. And then what we will do is we will discuss some of the results in this paper that you have. So please read that paper thoroughly, discuss it with your groups. I don't give you a lot of things to read, so when I give you something to read, I expect that you to read it. Thank you very much. And again, this book is the Economics of Education by Blair and I'll send out a link with it too, just in case anybody wants to purchase it, but it is not required at all to purchase it.